In recent years, experts have made groundbreaking discoveries that shed light on one of the most impressive feats of ancient astronomy: the Maya civilization's ability to accurately predict solar eclipses for over 7 centuries. This remarkable skill, reliant on acute observation and brilliant mathematical understanding, has been explained in a revolutionary study published in Science Advances. At the heart of this research lies the famous Dresden Codex, a critical artifact that contains intricate eclipse prediction tables spanning 405 lunar months. For a considerable time, scholars struggled to understand the complexities of this ancient manuscript, but new insights have finally unraveled the mystery behind its sophisticated system of astronomical predictions. The Dresden Codex is revered as the most complete surviving Maya manuscript and is crucial for understanding the astronomical prowess of the Maya. It has long been known to contain an eclipse prediction table, but previous attempts to decipher its secrets faced numerous challenges. The intricate nature of the table and the mechanisms the Maya used to keep their predictions accurate over generations were previously shrouded in ambiguity. The latest research, however, presents a fresh perspective that overturns many long-held assumptions about how the Maya maintained their exceptional accuracy in predicting solar eclipses. For the Maya, solar eclipses were not merely celestial events. They were ominous signs of divine conflict in the heavens. Illuminating the full astronomical significance of the Mayan calendar, researchers discovered that the 405-month cycle within this system was actually not designed specifically for eclipse prediction. Instead, it emerged from a lunar calendar that aligned seamlessly with the sacred 260-day calendar used for divination. The advanced statistical modeling utilized by the research team revealed that the length of 11,160 days in the 405-month cycle aligns more accurately with the 260-day calendar than with the cycles of actual eclipses. The sacred calendar played an essential role in the Maya's understanding of celestial phenomena, as priests used it to determine fates based on individual birth dates. The researchers explained that the Maya anticipated solar eclipses by correlating them with specific dates in their 260-day divinatory calendar. This intriguing relationship laid the groundwork for the evolution of the eclipse table, which emerged from the connection between lunar cycles and sacred time. By observing patterns of eclipses that occurred on similar dates within their religious calendar, the Maya were able to identify the mathematical relationships governing these celestial occurrences. The 11,160-day cycle consists of exactly 46 cycles of the 260-day calendar, demonstrating its significance for harmonizing calendars beyond merely tracking eclipses. Through the lens of hieroglyphic texts in the El Caracol Observatory at Chichen Itza, researchers were also able to glimpse further progress made by the Maya in the field of astronomy. The existence of eclipse pages in the Dresden Codex exhibits sophisticated astronomical calculations that cover a span of 405 lunar months, revealing the depth of Maya understanding of celestial events. One of the most compelling outcomes of the study is the solution to a long-studied question: how the Maya managed to maintain such remarkable prediction accuracy over a period of more than 700 years. Previous theories suggested that once a table covered 405 months, astronomers would simply begin anew from the end date. However, mathematical modeling against a historical database of actual solar eclipses visible to the Maya between 350 and 1150 AD unveiled a more complex approach. Maya astronomers employed a system of overlapping tables. They reset new cycles at precise intervals of either 223 or 358 months before the previous table concluded. This ingenious method allowed them to correct for small astronomical errors that would accumulate if tables were simply continued without adjustment. This innovative strategy ensured that predictions did not gradually drift away from the actual dates of eclipses. By restarting tables at these calculated intervals, with a ratio of 4 resets at 358 months for every reset at 223 months, the Maya were able to predict every solar eclipse visible from their territories for centuries. This level of mathematical precision is comparable to that of modern computational methods, all achieved without the benefit of telescopes, computers, or metal tools. The research also delves into how Maya astronomers recognize groups of eclipses, termed eclipse families. These families consist of eclipses occurring at intervals of 88 months. Notably, all 55 prediction stations articulated in the Dresden Codex belong to one of three distinct families, each following this consistent pattern. This systematic organizational principle, in conjunction with their recognition of the near recurrence of eclipses over a 520-day span in their sacred calendar, formed the backbone of the Maya's predictive capabilities. According to the research team, the observations made through approximately 3 complete passes of the 405-month cycle would have provided sufficient data for the Maya to develop this sophisticated framework. This implies that functional eclipse tables were in existence by around 550 AD. The achievement of the Maya's astronomical feats is even more impressive when considering the limitations they faced. They had no concept of a heliocentric solar system, nor an understanding of gravitational mechanics. Furthermore, they lacked optical instruments to magnify distant celestial objects. Instead, their success rested on meticulous, naked-eye observations and extraordinary mathematical capabilities. The Maya mathematical system, including the concept of zero and a base 20 counting system, facilitated complex calculations that spanned centuries. In their computations, the researchers noted that Maya astronomers utilized a precise ratio of 1,447 days to 49 months as their model for lunar cycles. This ratio proved to be accurate to within seconds when compared to modern measurements, enabling them to project lunar phases far into the future. The choice of a 405-month cycle highlights the profound understanding of numerical relationships that the Maya possessed. It represents the first month span within their counting system that equals a multiple of 260 days when calculated with their 1,147-day ratio. This mathematical elegance emphasizes that the eclipse table emerged not merely from eclipse observations, but also from the broader context of their calendrical studies. An analysis of the intervals between historically documented eclipses in the Maya region further shows an impressive concordance with the predictions made in the Dresden Codex. The most frequent interval identified between visible eclipses was 669 months, which corresponds to exactly 3 Saros cycles of 223 months. This triple Saros pattern became particularly valuable for predicting not only when eclipses would happen, but also for identifying when they would be observable from specific geographic locations. The classic period Maya would have witnessed this pattern repeatedly, bolstering their mathematical models with empirical verification. Experts now appreciate the sophistication of Maya astronomy, considering the constraints and limitations they faced. Their legacy continues to evoke awe and admiration as it showcases human ingenuity in deciphering the complexities of the universe long before the advent of modern technology.